This is another part of my series where I help fellow YouTuber Melissa Lucy pass chemistry. I designed a custom study plan for her and for you. You can get that free study plan using the link in the description. That study plan has several videos and other resources that I know will help you stress less and graduate faster. All right, let's get started. So this is the main thing I wanted to focus on, or all the different formulas. So as we mentioned before, we saw the relationship between our wavelength and then our frequency here. Now here it actually shows us that they are inversely proportional to each other, because if I were to kind of just look at it this way, like 1 over something like this just means that it's kind of like in relation to. So frequency in relation to our wavelength is inversely proportional. This like fraction just tells us that it's inversely proportional to it. And then the main formula here is actually just going to show a constant. So he said you're probably going to have to memorize the constants and the formulas. So this top one is definitely one to know. So I'll point out the main formulas that I recommend that you memorize. This first one is definitely one. This is going to help us figure out what the frequency is if we're given the wavelength, and vice versa. If we're given the wavelength and we're asked to find the frequency, we could also use this formula.
Okay.
The next one that I'd say is probably the most important one to know is this next one. So E just represents energy, H is Planck's constant, C is speed of light, so all of these are just different constants. And then once again, we'll have our wavelength. So this one is good to know because if we're asked to find the energy and we're given wavelength, then we can solve it using this equation, or vice versa. Again, if we're solving for our wavelength and we are given our energy, we can solve it using this formula.
Okay, and would that be like find the energy of one photon? Is that the same thing, or?
Yes, but at the end you'll have to divide by Avogadro's number, which we will go over an example like that.
Oh, okay.
Yeah, but good. You're catching on already. And then what else? The other equation that we have is just the frequency and the energy one. So this is our, I'd say the third one to know is we have our energy, we have our frequency, and then once again Planck's constant.
So then
the other thing that
I was just gonna ask. So I see that both 2 and 3 are like for the energy. So why would you use one over the other?
So let's say you weren't given the wavelength this time, but you were given the frequency. So if you're given the frequency and asked to find the energy, then it has to be number 3.
Okay, gotcha. Yeah. So it just depends on the question.
Yeah, no problem. So like if you're ever wondering, hey, which formula should I use? It's dependent on whatever they're giving you and whatever you're finding.
Got it. Okay.
And then let's see, I'd say this is the fourth one. We're technically going to have 5. This one is not common. So different, I'd say different states may use this, or even different countries. But I haven't, personally, I never did in my education. So I highly doubt that you will too. Let's see. So 4, we're going to go over in detail afterwards. I'm going to move on to number 5. And this is just looking at the number of photons. You will be asked, most likely, how many photons there are. And then remember, a photon is pretty much just a packet of light. We're just talking about light again. It's now just a little packet of it.
Okay.
Yeah, I know. All these little words.
Yeah, like, okay, whatever that means.
So, and all of these, again, like all these terms are good multiple choice questions. But like I said, like the main ones that you're going to see on your exam are just actual calculations. That's why I want to skip to let's just do calculations, because that's the hardest part. And then I'd say for this last formula, I just want to do it together because like I actually I wouldn't say I made up the formula, but kind of. It was just an easier way to have it always work every single time and actually give structure. So I'd say you're not going to necessarily find this formula in your book. I kind of just put it together because it made it easier for each step.
Yeah.
All right. So first things first, let's read the question and then identify what we're given and what we're finding and the formula that we're going to actually use. So I was nice and I put all the formulas up. I don't expect you to have them memorized yet, but eventually you will.
Okay.
So this is asking, calculate the energy of X-rays with a wavelength of 15.0 nanometers. So, knowing kind of what we know already, what is our given and what are we finding? Let me change this.
So,
Here we go.
we're given 15 nanometers.
Good.
And the formula we're going to use is E equals HC over the wavelength.
Perfect.
And we're finding energy.
You're good. Energy, yeah. Cool. Okay. So before we even go to the first step, the easiest thing that most people would do is just, hey, let's just plug everything into the formula and then put it in our calculator and we're done. And that would be wrong.
Wait, I think I know why.
Why?
Because we have to convert to meters.
Beautiful.
Okay.
Exactly. Yes. So here it may seem like, okay, cool, I get everything, but you're not going to just plug everything in. It's always going to be dependent on the different constants that you have. So I'd say, let me not change this to pink, blue. So for, let's say, H and C, so Planck's constant and the speed of light, this is in joules times seconds, and then our speed of light is meters per second. And then that's why they have to all cancel out, right? So that's why we have to convert nanometers to meters.
So will we always have to do that?
Yes.
Okay, good to know.
Yeah. And then same thing, you're going to see that with like frequency. Whenever it's like anything other than seconds, then you're going to have to change that, which we'll go over.
Okay.
So, okay, how do I convert this?
Yeah, we draw our little thing and then we would put 1 nanometer on the bottom is equal to 10 to the negative 9 meters.
Beautiful.
And then we multiply it across. So.
Yes.
Okay. You already have it. Okay.
Yeah. Yeah. This is what you got, right?
Yes.
Cool. Meters. Perfect. Okay. So now that is done, we're in the correct unit. Now you just plug it in.
Okay.
So that isn't too bad. Just using the formula that we found before. So E, let me set this all up. Are you also going to have to know the constant? Or is he giving that?
I think he's going to give us that. I think he just said that we need the formula.
Formulas?
I believe he's going to give the constant, but honestly, like I won't know until he sends out that thing and he tells us what he provides. Yeah.
Got it. And then I just wanted to highlight on one thing of the speed of light was C can be two different numbers. It could either be 2.998 or it could be 3. Doesn't matter. It's just dependent on whatever whatever your instructor actually tells you to use.
Actually, it's funny you should say that because I was just wondering that because in my lab we used 2.998 and then he did a problem in class today and he wrote it on the board as 3.0 times 10 and I was like, okay, I mean it's pretty close to each other but still.
It is.
Okay.
Like why couldn't we all just decide on one thing? It's kind of like that whole thought of like, hey, 4 out of 5 dentists, like who's that last person who couldn't make up their mind?
Exactly.
Then the wavelength, okay. All right, and then I just wanted to highlight on this before I even do the calculation, but just looking at this part, if we were to have not changed the units from nanometers to meters, it wouldn't all cancel out. Like here we have the seconds and this seconds that cancel, and then here if this was nanometers, that wouldn't cancel. We literally would have been left with joules per nanometer, which isn't anything.
Okay. So then how does it, so we end up with joules per second?
Correct.
Which is
Oh, just joules.
just joules, yeah, because the seconds cancel. So if everything cancels out beautifully to give you the actual unit that, you know, what you're finding of, like energy is in joules. So that's how you know you did everything right.
Got it. Okay, good.
So then you should have had, let's see, sig figs again come into play, 1.3252.
I'm still struggling with that.
How many sig figs do you think we would round to?
Well, we did multiplication and division, right?
Yes, but it's the same formula. It's the same formula though, because multiplication and division.
Oh yeah, it's the same one. Okay.
Yeah.
Okay, so it's the least sig figs.
Yes.
Okay, so it's gonna be 3.
Yes, because of the given, right? We're not taking it from 10 to the negative 9th. We're not looking at that. We're just looking at these 3. 1, 5, and 0. Cool.
Oh, I was looking at the formula that we just did.
Got it. That's fine too, because it's still going to be the same value, right?
Right.
We still had the same sig figs because we didn't change any numbers.
Oh, okay. I see what you're saying. Yeah. Okay.
Yeah, I typically like to just look at the given, not the constants, because that's not part of what we're given in this question.
Okay, that's good to know. So for any sig fig thing, just look at the given.
Yeah.
Correct.
You don't have to look at the numbers you dealt with unless you're doing like combining 2 different things, right?
Yeah.
Okay, great. Cool.
So then what would be the final answer here?
So we would get 1.33
Good.
times 10 to the negative 17 joules.
That's it.
Oh my gosh, I wish I would have known this like 2 days ago so that way in class I wouldn't have been so confused.
All right, next one. So this is where I was saying that we're probably going to have to convert more, or we're going to have to convert something else. So let's just start off once again reading the question and having our given formula and our whatever we're finding. So what is the wavelength in meters of an FN radio wave with a frequency of 102.5 megahertz? If you've ever wondered, this is your time to now wonder what an FM radio wavelength is. It's exactly what I do when I listen to the radio.
Yeah, me too. I'll never look at 102.5 the same. Okay.
What are we given? What's our formula? And what are we finding?
We're given 102.5 megahertz.
Mm-hmm.
And then would I also say that we're given that because we're already supposed to know that the 1 hertz equals.
Sometimes it gives it to you, other times it doesn't. It's honestly dependent on if your professor is feeling nice.
Okay.
Yeah.
So we're looking for wavelength. So I'm looking at the formulas really quick just to figure out which one.
Okay.
What are we given? We're given frequency.
Yes.
Frequency. So I want to look at, okay, what gives me frequency and a wavelength in the formulas?
Frequency and wavelength. The first one.
Yes. So that's how we choose. Yeah. So it might be easier to look at what are you given? What are you finding? And then, oh, yep, this has to be the only one. And then C, we already know is a constant that we know.
Okay, perfect.
So this has to be our formula. I want to make sure that people know this is not a V. That will change. Okay. So, first things first, this is not in the correct unit. How I know that is based once again on the constant. So let me put this in orange. So this C here is in meters per second. So it can't be in megahertz, it has to be in seconds. So, and specifically just to kind of make a note, this is seconds to the negative first. Whenever you have like 1 over a second, we can actually change that to an exponent. So that just means it's a negative exponent, so -1.
Okay.
That may look familiar coming back from algebra.
Yeah, I do remember that rule.
Okay. So that's why now we know that this has to be in seconds to the negative first. So that's why they gave it to you. But there's a little bit more work to be done here. So in this case, you're not just going from megahertz to just immediately to seconds to the negative first. We have to have multiple conversion factors for this. And we're going to pull out our our metric system again. It doesn't go away. I know. So let's just determine the different conversion factors that we're going to need to go from megahertz to eventually seconds to the negative first. So what should I convert this to first?
Oh my gosh. I guess from megahertz to hertz?
Yes.
Is that a thing? Okay.
That's a thing. That's a thing, yes. And then we would actually get the seconds to the negative first based on what we were given right here.
Oh, okay. I see now why that ties.
Yeah, that's why they gave it to you. But just in case, it's an easy one, I'd say, to remember since it's 1-to-1. So our first conversion factor just comes from the metric system. So I want you to identify, okay, what's mega, and then think about what goes where. So if we're looking at mega.
Oh, okay. So we would write, first we would write 102.5 megahertz.
Mm-hmm.
And then draw our little thing, and then we'd put 1 megahertz in the bottom, and then 10 to the 6 on top.
Beautiful. And then keep going.
And then, then we're gonna do 1 hertz on the bottom, and then 1 s to the negative 1 on top. Yay!
That's it. Yeah. Perfect. Okay, and then multiply straight across. That gives you, I wrote everything out already just to make it easier. Let's see. 1.025 times 10 to the 8th seconds to the negative first. Not done yet. That was just converting the units. I know. So the next thing is to figure out what the actual wavelength is. So I want us to kind of practice rearranging formulas. I'll show you 2 different ways. So I'm going to delete this just to make it a little bit easier. Let me not delete the actual step. All right, and then make room. Okay, so if I were to rearrange this formula, and the reason why I even care to rearrange this is because this is solving for frequency rather than what I'm actually finding, which is the wavelength.
Okay.
So, I don't know if you remember.
Yeah, I remember doing this in algebra. So would we have to multiply by the wavelength on the other side?
Good, because these cancel, yep.
Yeah, and then divide by the frequency.
Beautiful.
Okay, wow, I never actually thought I would use this like weird stuff from algebra where they would literally just do like letters or something and you would do it, yeah. But now I get it.
Yeah, it comes back, and it will come back again later this semester, multiple times.
Okay.
So this will come in handy. Okay, cool. Now that we have the right formula, now we can literally just plug everything in since we have everything in the correct unit.
So weird that you can just like rearrange and it will still work. Like it's just... so beyond me. Oh my gosh.
10 to the 8th, yeah. Cool, so I'll put our constant, so C, and then everything that we just found previously.
So is the C, we're not using Planck's constant yet, are we?
No, so Planck's constant is H, which we will do in a couple, I think the next example or the following.
Oh, okay.
The one after that.
So this is just called C, which is what?
The speed of light.
This is the speed of light. Okay, got it. Thanks. I'm just trying to like make sense of it.
Yes.
Yeah.
Yeah, this is the speed of light. Then I divide. This would give us 2.9268 and meters because these seconds cancel. How many sig figs do we round to?
Oh, okay. 4.
Good.
You scared me for a second.
No, I had to look. I was like, wait, what did we start with again?
Yeah, I know. I went like straight to the start. I'm like, I just learned that.
So what do we round to?
So 2.927.
Perfect. And then that's in meters. Cool. And then this just kind of like making a note here. This did tell us to leave it in meters. Luckily, since you're going to be given that pretty much on your multiple choice, like it's actually going to show the units. But typically I'd say they may have you take it a step further and have it stop at nanometers.
Okay.
So just in case if, like, I know that for this question we're done, but if you did have to change this to nanometers, what would you do?
We would put 1 meter on the bottom.
Yeah.
No?
1 meter on the bottom?
This is when we're going to use the 10 to the negative 9, right? Oh, so that goes on the bottom?
Because that's with the meter. And then the one with the nanometer, right? So...
Jeez, okay.
The 10 to some sort of value goes with the base unit, which is meters, and then the one that actually has the prefix has the 1.
Oh, yeah, okay. I get so used to, like, doing it the other way. You know, because we've converted, like, literally the last 3 conversions I've done, like, today and yesterday have been nanometers to meters.
And that's why I'm like, I like this trick, just because, like, if you think of it that way, you're never going to get it wrong. You're never going to question, is it on the top or on the bottom?
Right. Okay, so it always goes with the one with the base unit. Okay.
Cool. And then this would have just been 2.927 times 10 to the 9th nanometers.
Cool. Okay.
Yeah, if you were asked that. Next one. This was the energy of 1 mole of photons. So let's understand what in the world that means. Starting off, this is saying if the wavelength of a photon is that, what is the energy of 1 mole of, and I'm going to say of photons. Let's see if I can add an S there. Because a photon does not make sense. Of photons. Okay, what are we given and what are we asked to find?
Okay, we're given 552 nanometers.
And that's a wavelength.
And we're given...
Don't worry about the formula for now.
Okay, so we're being asked to find the energy.
And then this is where it's a little bit different. So our units are going to change because it's not just saying, what is the energy? It's actually saying, what is the energy of 1 mole of photons? So instead of just like joules, it's actually going to be joules divided by moles. So joules per mole. That's what we're going to want to get at the end. So there are multiple steps with this one. I would start off with just converting. Right, it's not in the correct unit. If we're starting off with nanometers and we know we have to use some sort of formula, then I have to convert this to meters. So let's just start off with, what would the original formula be if you were just asked to find the energy and you were given wavelength?
It would be E equals HC over the wavelength.
Perfect. Okay, and then I'm going to start off with just converting again. So I know you know this one.
Yes.
Where the 1 is on the bottom, 10 to the negative 9th meters is on top. And then this would just give us meters. So 5.52 times 10 to the negative 7th meters. Now that we have that, we can just plug it into our formula and solve for the energy. So let me make more room. Yeah, a lot of these pretty much are just like plugging in, and it's always just making sure that your units are correct. Half of the time, that's what it is.
Okay.
Do 6 times that. So I am using Planck's constant now.
Okay.
Since that was H. And that's 8, okay. And then we divide this by our meters. Copy. Perfect. Almost there. This gives us 3.60 times 10 to the negative 19th.
Yes.
Joules, since all this cancels. So almost done. We got our joules. Now we need the mole portion of this. So if we wanted to get a little bit technical, which you might see this, this actually told us that this is the wavelength of a photon. So this is kind of saying, okay, this is the wavelength, so nanometers per every photon. And I personally am not a huge fan of that, but just in case you may see this in class, and I say that because it's this last step. It's this last step that kind of seems a little bit strange. But if we're specifically looking at 1 mole, we remember that Avogadro's number is that one that allows us to go to particles, atoms, all of these different things. And it also allows us to basically go to photons. So in this case, what I would have to do is multiply this by Avogadro's number. So I'm going to take the energy that we just found. So here, and then all I have to do now is simply, let me set this up. Multiply by Avogadro's number. So this is 6.022 times 10 to the 23rd. And now this is photons per every 1 mole. So that's how we get that mole on the bottom. And then with the whole photons thing, it's really just, oh, here, I started off with nanometers per photon. So this also would have given me meters per photon. And then same thing here, this would have given me joules per photon. So just in case you're wondering, hey, what happened to like the photons? Wouldn't this have still had that photon unit there? Technically, no, it does cancel out.
Okay. So we end with just
joules per mole.
Oh, I see. Okay.
Yeah. So like just in case you're like, wait, but how did we just randomly get photons? How do we get rid of that? Technically, we started off with it. And that's what was showing like this part.
Okay.
Yeah. And then that would give us, here, let me make room. That would give us a very large number, but then we'd have to change this into scientific notation, which it might have already done on your calculator.
Mine didn't, but I know how to make it do it for me.
Cool. Yeah, or we can move this over 1, 2, 3, 4, 5, 2.16, 10 to the 5th. How many sig figs do we round to?
3.
Yes. So our final answer is 2.18 times 10 to the, not 18, 17.
Yes.
10 to the 5th joules per mole. So it's really that additional step. So if you're just asked to find the energy, you would stop at step 2. So it'd stop here. If you're asked to find the energy of 1 mole, then you would multiply by Avogadro's number.
So anytime you see it asking about mole, for anything, we know that it's Avogadro's number, right?
Yes.
Okay.
Next one is asking us about photons. So now we're going to use that formula that it's like I don't want to say I created because I have seen certain ones before. They just typically don't give you this or teach this specifically that way. But I'll kind of explain how to use this formula. This is, I'd say, 2 different formulas that we're going to use. Let's just start off with understanding what we have and then what we're finding. So how many photons are contained in a flash of green light? And it gives us 525 nanometers. That contains 189 kilojoules of energy. So let's just start off. What are we given?
Okay. We're given 525 nanometers for wavelength.
What does that represent? Yeah.
Wavelength.
Yes, sorry. I was like, oh, you really said it.
And then 189 kilojoules of energy.
Yeah. So that specifically, I'm going to just call this the energy that's given. Simple enough. Okay. And that's where I get this top part. It's just the energy that is given. Because they literally give it to you in the question. And then what are we finding?
How many photons are, or just photons? Yeah.
Just photons. Yeah. I would even say like, hey, it's just the number of photons. That's all it is. So if you know, we definitely are using this formula, the number of photons, because that's what we're looking for. We are given the energy of that the energy that's given, right? The energy of the flash of green light. And then what we don't have is this last part. So we don't have the energy of our photons, but we do have the wavelength of our photons. If you notice that first part, that's what this is. This is essentially telling us that, okay, we have that. So I need to figure out that energy before I plug it into the formula.
Okay.
So there's technically two formulas that we're going to use. We're going to start off with just, okay, the typical energy formula that we did before when we're given the wavelength. So that HC divided by our wavelength. And then the last thing is this formula that I have on the bottom. I'm just going to say the number of photons is then equal to the energy that's provided, so given, and then the energy of the photons, which is what we're essentially going to find in our first step.
Okay, got it.
So if we're looking for the energy of our photons, given this wavelength, can we just plug everything in? Or do we have to do something else?
Oh, we have to convert it.
Yes. I'd say get used to converting things.
Yeah.
Cool. So we've done this already. 1 nanometers on bottom, 10 to the negative 9th meters on top, 5.25 times 10 to the negative 7th meters is what we would get.
Perfect.
Next step is just to actually plug it into this top formula. So plugging everything in again. We have Planck's constant, 6.626 times 10 to the negative 34th, joules times seconds, speed of light, meters per second, and then what we just found, our wavelength in meters on the bottom. Okay. I need a tiny bit more room. I accidentally deleted that. There we go. Okay, and I'm running out of room. Let me erase some stuff. All right, I would get next page 3.7862 times 10 to the negative 19th joules, and then I can keep going from there. So the next step is using the second formula. So I now have the actual energy of my photons. That's what this is. And then now I can just plug everything in. And if I did that, it would be wrong. And the reason why it would be wrong is this is another thing. This is another place where they actually can get you again. Look at our units. This is joules, and what's given is kilojoules. So those have to be the same units again. So always pay attention to your units whenever you're plugging in values. If ever you don't have the units cancel out when they should, that should tell you I did something wrong. I need to go back.
Right. Okay.
So I'm going to convert the given amount of kilojoules. So 189 kilojoules, I'm just going to convert that to joules. What goes on top? What goes on bottom?
Okay. 1 kilojoule on the bottom.
Mm-hmm.
And I don't know this metric, but let me look. I have my thing right here. 10 to the 3. Okay.
Joules, perfect. And this gives us 1.89 times 10 to the 5th joules. So next we can, and then I actually can go back, just a little note. I can round this already. Like going back to that joules, that step 2, I can round this. We know that there's going to be 3 sig figs, right, based on what we're given as well. So I would just stop here, and that would have been 3.79 times 10 to the negative 19th joules, and that's what I can plug in.
Oh, okay.
So then I'll plug it into that formula where there's the number of photons equals these two divided. So on top is going to be the given. Our given was this one. So 1.89 times 10 to the 5th joules, now that it's in the correct unit, and then divided by the what we actually found in the beginning, the energy of our photons. This then gives us a large value. So 4.9868 times 10 to the 23rd. Once again, I'm going to round to only 3 sig figs. So I'll round up. 4.99 times 10 to the 23rd. Don't forget your unit. What it is, it's just photons.
Wow, that was a lot of work. Okay.
It was, yes. So this is, I'd say, I mean, I know there's multiple steps here, but typically it's just 2 steps. So what I want you to look at is just the formulas that you're gonna use. So before you can just plug it into this second formula, you have to have the actual energy of the photons, and that's what you typically find first, and then you can plug it in. The reason why we had so many steps was just we had to convert 2 different units.
Okay.
Questions here?
No, I think it's straightforward.
Okay. I hope you're enjoying the series so far, and if you need additional help, then head on over to melissamariville.com, and I'll see you in the next video.